Okay, so the first thing I suppose I wanted to point out to you today is just how close we are to finishing this topic area. So we're concentrating today on calculations of force, momentum, acceleration and weight, plus a few others from year 2 content. That means we've already covered net force, balanced and unbalanced forces, weight, reaction, um, friction, air resistance, factors affecting friction and air resistance, and then manipulation in sports performance. We've looked at free body diagrams showing vertical and horizontal forces, definition of centre of mass, factors that affect the position and centre of mass, and the relationship between centre of mass and stability. So after today's lesson, where we're going to look at force, momentum, acceleration and weight, all we have remaining in this topic area is Newton's laws before you'll sit your next end of topic test. So calculations questions. We're going to do a lot of calculations today. I know lots of you might not think of yourselves as mathematicians. The maths here is not really complicated maths at all. And in fact, often the quantities that they give you in the exam can be calculated without a calculator. Saying that though, we need to make sure that we bring a calculator to your physiological factors affecting performance exam, and that is because you don't want to make any mistakes. You don't want to be wasting time calculating on paper when a calculator is allowed. So make sure you bring a calculator to the exam. Really, the main difficulty in this section is remembering all the equations rather than actually carrying out the calculations themselves. Okay, so for these calculation questions, they allow you to pick up valuable AO3 marks. We've looked at this table before. Remember, AO1 marks are for demonstrating knowledge and understanding, AO2 marks for applying that knowledge and understanding, and AO3 marks for analysing and evaluating. And what the calculations questions get you to do is analyse. Very often there might be a table with data in it, or a graph with data, or you're just given the quantities, but you need to analyse those quantities somehow, whether it's the table or the graph, in order to get the data to put into your equations. And that skill is analytical, and therefore it helps you to pick up AO3 marks. To pick up those marks, we need to make sure we write the equations at the start of every question, then put the figures into the equation, and then produce your full answer. And we're going to produce that full answer using a calculator, not forgetting to include the units. Okay, so we're going to work through each of these now: force, momentum, acceleration and weight, and then have a look at the ones that I've shown you that come really into year 2, but hopefully you'll see why we need them now. Okay, so first one then is force. You give yourself a subheading force and rewrite the definition. You've looked at this definition of force before: a push or a pull that alters the state of motion of a body. It's calculation you need to know. Force equals mass times acceleration. And I do like to use these pyramids. I know probably the mathematicians amongst you won't like these pyramids, and the maths teachers probably wouldn't like it. But I think for this level, and remembering the calculations, these pyramids can make things a little bit easier. So wherever we've got a times by, so something equals one thing times by something else, we can use this triangle to help us rearrange the equation. If I know and memorise the equation for force, then I can automatically work out the equation for mass and the equation and an equation for acceleration. Okay, so if we put force at the top, because we want the two things that times by each other along the bottom, mass and acceleration, we can then rearrange it. If I wanted mass, then I do force divided by acceleration, and if I want acceleration, I can do force divided by mass. So that's worthwhile remembering. We're going to look at another equation for acceleration today, and it depends what data you're given as to which equation you would use. Okay, but I personally find these triangles quite useful. You might want to note that down if you've not used it before. Okay, so Usain Bolt has a mass of 94 kilograms and accelerates at a rate of 6.41 meters per second over the first 20 meters of the race. Calculate the force required. So the first thing I'm going to do always is write out the equation. So force equals mass times acceleration. Okay, now even if I make a mistake now, let's say I put in 49 instead of 94 down here because I'm under the exam conditions, then I may well have picked up a mark just for knowing the equation. So it's absolutely worthwhile writing the equation out first. So we're going to put in the figures. So mass is 94 and we're going to times that by acceleration, which is 2.41. And that's going to give 226 point, I'm just calculating that there, 226.54, and then really important, like the units, which in this case is newtons. Okay, we must not forget. Now if we were marking this question, we'd have picked up a mark right at the top for knowing the equation, and we'd then pick up a second mark for coming out with the correct answer in the end. Okay. So the next one is acceleration, and it's the same equation really for deceleration as well. We'll look at deceleration next year, but essentially when we do this equation, if we get a positive number, then it means we're seeing acceleration. If we get a minus number, it means we're seeing deceleration. All the ones that we're going to deal with today are acceleration, are going to be positive numbers. So acceleration, the rate of change in velocity, and we're going to take a look at velocity later. So yes, we did just say that acceleration could equal force divided by mass, but actually it's more likely in the exam that they're going to give you the velocities, some split times, and final and initial velocities. Okay, so it's essential that we also know this calculation. So acceleration is final velocity minus initial velocity over time, and we'll work through a few examples to show us exactly what we mean there. So when Usain Bolt achieved his personal best, his split time over the first 20 metres was 2.88 seconds. The split time is how long it took for that period of the race. So they might give you 20 metre sprints for 100 metre, in which case it would give you the time taken to run the first 20 metres, then the second 20 metres, then the third 20 metres, or it might be 10 metre split times. But a split time essentially is how long it took you to do that little bit of it, that portion of the race itself. So his average velocity when he reached that 20 metre mark was 6.94 metres per second. Calculate his average rate of acceleration. Okay, so again, I'm going to write it out. Acceleration is final velocity minus initial. And then I'm going to divide that by time. It's essentially the change in velocity. How has the velocity changed over that period of time, which is the acceleration? So in this case, then final velocity is 6.94. So let's put that in. So 6.94 minus the initial velocity. Well, this is the first 20 metres of the race, so his initial velocity is 0, okay, which gives us obviously 6.94. And then we need to divide that by the time. So 6.94 divided by the time, which was 2.88, gives 2.41, and then again we must not forget meters per second per second. So on your reading that you did beforehand, you were asked to you will work through that example and then asked to calculate the accelerations of the following. Okay, so let's have a go at those. I'm not going to get rid of the equation, so I don't have to keep writing it out. So this first one, the average velocity was 6.37, and the time was 2.97, remember, for that 20 metres. So I would take the final velocity, which is 6.37, and minus the initial velocity, which was again 0, which gave 6.37. And then obviously we go 6.37 divided by the time, 2.97, which gives 2.14, and again meters per second per second. After I've done each one of these, by the way, just pause the video and check that you got it right on your reading when you tried out the calculations before watching this video. The second one then, we would go 5.62, again minus 0 equals 5.62. 5.62 divided by 3.34 equals 1.68. Again, don't forget the units, meters per second per second. And the final example that you should have worked through in the preview reading is so this one was 6.09 was the final velocity. Initial velocity was 0 again because it was the start line, it was the first 20 metres, which obviously means the change in velocity is 6.09. So 6.09 divided by 3.17, which is the time, gives us 1.92 meters per second. Okay. Now then, in all these cases, the initial velocity is 0 because it's the first 20 meters of the race. The exam might give you the second 20 meters of the race, give you the initial velocity and the final velocity of that second 20 meter split, in which case the initial velocity is not going to be 0, but the calculation is the same. Final velocity minus initial velocity to give you your change in velocity, and then that divided by time gives you your answer, your acceleration, your rate of acceleration. That's probably the trickiest calculation because there are 2 stages to it, and especially if you had to work out final or initial velocity, which I'll show you how to do later in the video. Okay, so next one, momentum is the quantity of motion possessed by a moving body, and the equation is mass times velocity. So again, we could do momentum, put it into one of these, mass times velocity, and if they asked me for mass and gave me momentum and velocity, I should be able to calculate that knowing the equation momentum is mass times velocity. So if I wanted to know velocity, it will be momentum divided by mass. If I wanted to know mass, it will be momentum divided by velocity. But I only need to remember this one, okay? So momentum is measured in kilogram meters per second. That's because mass is measured in kilograms and velocity is measured in meters per second. So we just sandwich those 2 things together to give us kilogram meters per second. It's the same up here, actually, sorry, because the change in velocity is measured in meters per second and time is measured in seconds, so we get meters per second, okay? That's a way of sort of working out the units if you can't quite remember what the units are. So Usain Bolt scored a personal best time of 9.58 seconds in the 100-metre sprint. He weighed 94 kilograms and had an average velocity of 10.44 metres per second, calculated as momentum. So this is a bit of a tricky question here because they've given you some information that you don't need to know. All you need to know is mass and velocity. So I'm going to make sure I write out the calculation first. So momentum is mass times velocity. Sorry, the equation first. And then momentum equals mass, which is 94, times velocity, which was 10.44. And that gives me 981.36 kilogram meters per second. Okay, again, you had some ones to calculate on the pre-reading, so if I go through them, make sure you pause the video and just check that your workings out on the reading before this video. Check that you did them correctly. So the first one, again, you had to calculate the velocity. You would have calculated the velocity already, so I'm going to go through the velocity answers here as well. So the velocity for the first one is obviously 100. So velocity is a displacement over time. So 100 divided by 10.34, which gives you 9.7. And then we're going to take that 9.7 and put it in this. So that was the velocity. So then it's 80. So the kilograms, the mass is 80 times the velocity, which I've calculated to be 9.7, equals 776 kilogram meters per second. So that would have been your answer to number one for both the velocity and the momentum. Let's add the equations this time to make sure we're being clear. So the second velocity example that you were asked to do at the start, so velocity equals displacement over time. So the velocity of this athlete was 100 because they ran 100 meters, divided by 9.97. Their velocity equaled 10.03 meters per second. And then if we go on to the momentum, so momentum equals mass times velocity. It's 80 kilogram mass again, times their velocity, which was 10.03. That equals 802.4 kilogram meters per second. And the third example from your readings, again, pause the video, go back if you're not sure, watch it again. We had this athlete, so they'd run 100 meters was their displacement. Their time was 11.45, and so their velocity equals 8.73. To calculate their momentum then, they had a mass of 80 kilograms times by the velocity 8.73, means their momentum is 698.6 kilogram meters per second. Okay, so that's the worked examples on your preview reading for velocity and for momentum. And finally, weight. Now this should feel, sorry, I haven't looked at this in your preview reading. This should feel like you know this already, because we looked at weight when we looked at the force arrows. So we define weight as a downwards force. So the downwards force acting from the centre of mass of a body due to gravity. And we already looked at this calculation. Weight equals mass times acceleration due to gravity, measured in newtons. So we said that weight is that force that's acting downwards from the centre of mass of a body, and it exists due to gravity. It's always present where there is gravity. And we said previously that weight is mass times acceleration, and that in PE, it's good enough to say that acceleration due to gravity is 10 meters per second. If you're studying physics, then you're probably going to use a number that's to a number of decimal places. But for us in PE, 10 meters per second is fine. So you previously calculated these. A cyclist of 68 kilograms a sprinter of 82 and a marathon runner of 62. Well, weight is mass times acceleration. Their mass is 68, so 68 times 10 would obviously equal 680, and weight in newtons again. Okay, so that's our weight calculation. So that's the year one stuff. If we go back, force, acceleration, momentum, and weight. But we're going to add on a little bit of year two stuff. And the reason for that is that some of these things we need to know for these equations. Now, distance, we don't need to know for any of those previous equations, but we do need to know about distance in order to calculate speed. But displacement, we need to know about displacement in order to calculate velocity. Now, we've used that velocity quantity in a few of the examples previously. We need to know about velocity to calculate acceleration and to calculate momentum, which is year one stuff. So I think it's useful now to look at velocity because that helps us understand acceleration and momentum. Similarly, acceleration appears on the year two specification as well, and we need that acceleration to calculate force, which we've just done. So I think it makes sense to look at these quantities now rather than to leave them for next year. Next year then they're just revision. Okay, so let's look at the distance, the difference between distance and displacement to start off with. So distance is the total length covered from start to finish positions measured in meters, and displacement is the shortest straight line route from the start to finish position, again measured in meters. Let's have a look at an example. Okay, I don't know what this would, maybe the course of a marathon. Okay, so this is the start point, and this would be the route that the runner took. Okay, around streets, whatever. This would be the finish position. If it were the marathon, then that would be about 26 miles, even though it's measured in meters. I'm not sure how many meters is in 26 miles. Anyway, the point is displacement then is something completely different. It's the straight line, the shortest straight line between the start and finish. So the displacement is that there, okay, that line there, in that shortest line from start to finish. So even though that route might be 1,000 meters, the distance from start to finish, once a runner has moved from the start to the finish point following the route, their displacement might only be 400 meters. Okay, we might have a route here that is 100 meters, but actually once the athlete has covered that from start to finish, their displacement might only be 1 meter. Okay, so that's the difference between distance and displacement. It becomes interesting on things like a 400-meter track and a 25 and 50-meter swimming pool, because the distance and displacement are then very different. So on a 400-meter track, when a runner completes the 100 meters from B to C, their distance is 100 meters and their displacement is also 100 meters. When the runner runs the 300 meters from B round to A, their distance travelled is 300 meters, but their displacement would be whatever this is here. It's not sure. Oh, I need to do Pythagoras. 31.831 meters. Okay, that's not right, is it? For the 400 meters, the distance is 400 meters, but the displacement is actually 0 if you're running on the inside lane. If you start where you finish, then the displacement is 0. Okay, so speed then. If we use those quantities, speed is the rate of change in distance. So if the question's about distance and it's giving you the distance travelled by an athlete, then the quantity that you can calculate from that is speed. Whereas if a question gives you displacement of an athlete, then the quantity that you're going to calculate is their velocity. So that's the difference. Speed is about the rate in change of distance, and velocity is about the rate of change in displacement. Both of them then take that quantity divided by time. So speed is distance over time, velocity displacement over time. Both of these are measured in meters per second because distance is measured in meters and time is measured in seconds. So we sandwich those two together to get meters per second. Displacement is measured in meters, time is measured in seconds. So again, we sandwich those together to get meters per second. So if you can't quite remember the units for speed and velocity, that's a good way to work it out. So speed, the rate of change in distance. We know that speed is distance over time measured in meters per second. Calculate to one decimal place the average speed of a skater who covers a distance of 400 meters in 27 seconds. So we would write that we know that speed equals distance over time. And then put in our numbers. So 400 is the distance. It took them 27 seconds, which means that their speed is 14.8 meters per second. Without the unit, I'm not getting any marks here, okay? So if we came to mark this, it's a mark for knowing the equation and a mark for getting the correct answer, which must include the units. If you'd just put 14.8, then you wouldn't get a mark. Okay, so velocity this time then. The rate of change in displacement. Usain Bolt's PB for the 100 metres is 9.58 seconds, calculated average velocity. So Usain Bolt, so velocity equals displacement over time. His displacement is 100 meters, his time is 9.58 seconds, and so his velocity is 10.43 meters per second. On your preview reading then, you needed to calculate the velocities of the following athletes. Okay, so we'll do that again. We'll do that together now. So velocity is displacement over time. The first one is 100 over 10.34, which gave you 9.67 meters per second. The second one is 100 over 9.97, which gives you 10.03 meters per second. And the third one, displacement is 100, 11.45 is the time, which gives you 8.73 meters per second. So you can go back and check up those three from your preview reading. And just like we did before, again, with the velocity is displacement over time, we can do velocity, sorry, that's wrong. If displacement over time is velocity, then velocity times time is displacement, and displacement divided by velocity is time. So again, you can rearrange that equation. A different one now. So calculate to one decimal place the average velocity of a swimmer completing the 400 metre freestyle in a 25 metre pool in 4 minutes and 59 seconds. Now there are two difficulties to this question. First one, we need to calculate the displacement. So 400 meters in a 25 meter pool. If this is the start edge of the pool, we're going to swim 25 meters, 50 meters, 75 meters, 100 meters. So after 100 meters, we're back to where we started. That means after 200 meters, we're going to be back to where we started, and after 400 meters, we're going to be back to where we started. So displacement in this is going to be 0, okay? The time we need to calculate in seconds. We can't put 4.59 in because time is measured in seconds. So 4 minutes and 59 seconds is actually 299 seconds. But 0 divided by anything is just going to be nothing, okay? So if in a displacement question your athlete is finishing where they started, the answer must be 0, because 0 divided by anything is 0. Okay, so that's it. We've been through the quantities in year 1. We've now looked at distance, displacement, speed, velocity, and we'd obviously already covered acceleration. I would go back, look through that preview reading again and make sure you're clear with all the examples. Go back through the worked examples and then have a go at the homework calculations.